During the previous lesson, we discussed how we can build a small circuit that could function as part of the arithmetic and logic unit of a CPU, and then how that circuit can be used to carry out one operation, for example, the addition operation of two numbers. Few minutes ago, we looked at how those operations can be put into CPU instructions, which can be executed through a CPU instruction cycle. Now let's try to combine these two concepts and see how the internal components of a central processing unit is organized in such a way that the CPU can execute a program or a sequence of such instructions by repeating instruction cycles. So we look at what are the major components inside the CPU and how they are organized and interconnected to perform this task. We already know that the arithmetic and logic unit is one of the very key components in the CPU. It is a collection of circuits which can carry out different tasks or different elementary operations that the CPU is capable of performing in. The ALU has two inputs and one output. Now both these input has to be provided with the correct data values when the ALU executes some operation. For that, the CPU will use some temporary storage locations, what we call registers. In a typical CPU, there will be few registers, not only one or two, but few registers to support that. Why we need few registers? Because it's very likely that the CPU will be doing sequence of activities and the ALU will be needing multiple operations to be carried one after the other, and the data that are needed for these operations can be held within the CPU without using an expensive memory read cycle for each of such operation. So in the example CPU that we are talking here, we have three such registers which we have named as register B, register C and register D. Each of these registers is capable of holding one binary value, one data element, and providing that with one input of the CPU. So you will see in the diagram that all three registers are connected to one of the inputs of the ALU. Even though all three are connected, they will not provide data. All three of them will not provide data at the same time, but instead they will provide data at the ALU input only when the control unit commands them to do that. Then what about the other input of the ALU? Now here you will see that it is connected in a particular special way. The second input of the ALU is connected to a special register called register A, or the register called accumulator. Not only that, the output of the ALU is also connected to the same register. So the register A or the accumulator register is connected to one input of the ALU as well as output of the ALU. Now this configuration has certain special features in terms of the instruction set that the CPU has, or more specifically how the operands of the instruction set can be specified when the operation involves or the opcode involves operation that is carried by the ALU. Since the ALU output is only connected to register A, the output operand of any instruction that involves the ALU has to be register A. Or in other words, whenever ALU carries out some operation, its output will always be stored in register A. The register A will be the one which receives the output of any ALU operation. Also, whenever ALU carries operation which requires two inputs, one of the two inputs must come from the register A. So in this case, the register acts as both input to the ALU as well as output to the ALU. It provides one input, and when the operation is completed, it stores the output also. So you can look at this like in a cycle. It has the input and then becomes the output. Again, for the next instruction, it can become the input and again the output. So because of this only, it's called the accumulator, because it accumulates the ALU outputs. Then the flag out register of the ALU is also here. Now in this case, the flag has 4 flags. One is called the N flag, the other one is called the Z flag, the other one is called the C flag, and the other one is called the B flag. In this context, the N flag refers a negative result. So if whenever ALU carries out an operation, if that operation results a negative value, then this N bit of this particular flag register will be set to 1. If there's a 0 output, that means the result is 0, then the Z flag of the register will be set to 1. If there's a carry forward to the next stage, then the C flag will be set to 1. Carry forward means an overflow to the next stage of the operation. Right? Then the C flag will be set to 1. If there's a borrowing from the previous stage, when you do a subtraction operation, for example, then the B flag will be set to 1. So this 4 bits of this particular register, the output register, the status register, will indicate what are the outputs, what are the status of the current last operation that is carried by the ALU. Then we have 2 other special registers in the CPU. One register is called the program counter. Now program count is also a very special register because it keeps track of where the next instruction is in the program. Always at the beginning of a CPU instruction cycle, when the CPU wants to bring an instruction to the CPU from memory, it first looks at the value of the PC register. If the PC register has a certain address, then the CPU uses that address to access the memory and bring the instruction that is at that particular location as the next instruction to be carried out by the CPU. Because of that, in some designs, this program counter register is also referred to as the instruction pointer register or the IP register. Now, each time when the CPU carries out an instruction cycle, the program count has to be updated to point to the next instruction in the program. Because that's how the CPU keeps on getting next instruction in each cycle and carries on this process. Now, since this updates happens very frequently, it usually involves adding a number to the program counter because you update to the next instruction by adding the length of that instruction to the previous address. In most designs of the CPU, to support this case, a special ALU is provided. Because otherwise, if I do this operation to the regular ALU, it will consume more time. So, to support this addition of this instruction length and updating the program count on every instruction as part of the instruction fetch itself, most CPUs are provided with a small ALU near the program counter, which is directly connected to the program counter. Then we have another special register called the instruction register. Now, whenever CPU brings an instruction into the CPU, it has to keep that instruction somewhere until the operation is completed. So that place is the instruction register. So whenever the CPU reads the instruction from the memory as part of the instruction fetch cycle, component of the instruction cycle, the instruction goes and landed in the instruction register. So then the CPU can decode it and then generate the necessary signals to carry out the instruction. Now, where these signals are generated? Now, for that, there's a special module that we have not discussed so far called the control unit or the CU. This component is responsible for generating different signals that the CPU internal components as well as the memory would require in executing instruction. Now, for example, when you do a memory read cycle, we saw that there are multiple signals to be generated. For example, you have to first send the address through the address bus, then you have to activate the read signal, and then you have to tell the component responsible for reading from the data bus to read the signal, etc. Similarly, in our earlier lessons add operation, we knew that there should be multiple signals. For example, first you have to enable the outputs to the inputs to the ALU, then command the ALU to carry out the operation, and finally get the output register to save that value in the output register. Likewise, there are multiple signals that need to be generated according to a particular sequence, a predefined sequence that depends on the instruction itself. So these timing signals and control signals are generated by the control unit. So it's like the nerve center of the CPU which coordinates the operations with other modules or other components that are in the CPU. So because of this, you will see that the instruction register is directly connected to the control unit. Because when the instruction is loaded into the CPU, the control unit can have direct access to the instruction that is in the instruction register. So it can decode the code and then decide on what actions to be followed next. Similarly, there will be control lines going out of the control unit to each and every register, component, etc. in the CPU. Now, for the control unit to operate, it needs some sort of a rhythm signal, like a heartbeat. Now, that comes from the clock signal and the clock generator. Usually, the clock generator is outside the CPU, it gets that as an input. So, the clock signal is special compared to other signals because it is periodic. It's like the heartbeat. At every cycle, it goes up and down, and during every cycle, the CPU carries out one action in the instruction cycle. So, faster the clock usually means higher the actions will happen in the CPU. Not always, but usually a CPU running at a faster clock will run faster. There are other things also that affect the CPU performance, which we will not discuss right now. Then finally, all these components in the CPU has to be interfaced with external components. In most cases, or at minimum, it need to be connected to the memory. For that, the connection is made through the system bus. So there should be one other module in the CPU which can coordinate these activities with the bus, and that is called the bus interface unit or the BIU. The bus interface unit handles two parts. First, it handles the electrical compatibility with the external bus and the internal component of the CPU in terms of the voltages, the signals that are required, etc. Second, it coordinates the timing of external events. It decides when to activate the read signal, when to capture the value from the data bus, when to put the address in the address bus, when to put data into the data bus, etc. All those timing requirements are also handled by the bus interface unit. So these are the primary components that makes part of the CPU. Now each of these components has a role, right? And all, for example, the ALU is responsible for carrying out the arithmetic and logical operations. Control unit generates all the controlling signals to other modules in the CPU. And registers are there to keep and hold the values temporarily, data values temporarily, so that they can be routed to the ALU for operations whenever required. And some registers have special purpose like the program counter and the instruction register, which are not used to store data but used to store other control information about the program. Also, the pattern in which these components are connected will also have some implications on the instruction set of the CPU. Now, for example, as we discussed earlier, in the ALU, this particular demonstration here, the output is connected to the accumulator register, which means that any instruction, any CPU instruction that involves the ALU operation should always has the accumulator register has its the output or the destination register. And also we see that one of the two ALU inputs are connected to the register A only, accumulator register only, which means that whenever you carry an operation using the ALU, one of the two inputs should always come from the accumulator. Now suppose you want to add the content of the register B and to the content of the register C. Now in this particular design of the CU, you will not find an instruction which says add B, C. The reason is that there's no mechanism where you can enable input of the register B to one input of the ALU and the register C to the other input of the ALU to do this addition operation. Instead, you have to carry out this addition in two steps. One will be to load either register B or register C to the accumulator. Copy a value of that register to the accumulator. And then add the second register with the accumulator to get the answer. For example, I might first have to execute an instruction called load A, C. which will load the contents of register C to register A. And of course, according to this design, that too has to be routed through the ALU. Right? So in this case, the ALU will receive one input, the ALU will receive the value of the register C. It will not do any processing to that, but simply pass it through to register A. So that's my first instruction. The next instruction, when I say add A comma B, the ALU, the other register B will be enabled to do in one of the ALU inputs. The accumulator A is already available in the other input of the ALU, which is held in the previous value of the register C, and then the add signal will add these two numbers and send the result to again back to register A. So if I want to put that result back in memory, for example, I have to route it back from register A to the memory through a separate third instruction. So likewise, the way the components inside the CPU are organized also determines what instructions that the CPU can support. In very simple CPUs, there will be only few instructions because there will be few combinations of modules that can handle those instructions. But in more larger complex CPUs with lot of registers, etc., there can be different variations of instructions handling all possible combinations of those registers.